When solving a system of linear inequalities, we follow all of the same steps that we do to graph one inequality. Except with a system, we're going to have two graphs on one grid. So here in our first slide, we have two separate graphs. Y is greater than 2x minus 1, and y is less than or equal to negative 7 over 2x plus 3. So what a system is if I would take both of these graphs and put one on top of the other. So if I drag this right graph on top of the left graph, you'll see that both lines and both shadings are on one grid. Now where these two shadings overlap, so where it turns a light shade of purple, this is what we consider to be our solution area for the system. We have solution areas for each line, but for a system, it's where both of those shadings will overlap. So let's look at our next example. We have y to be greater than or equal to 2x plus 6, and y is less than negative 3/4 x minus 5. So you want to complete one equation at a time. So we'll graph an equation and we'll shade an equation before we move on to the second one. So if I start with my first equation, my y is greater than or equal to 2x plus 6. I have a slope of 2, and I have a y-intercept of 6. So I'm going to start plotting my graph at positive 6 on the y-axis. And then since I have a slope of 2, remember that's like 2 over 1, so I'm going to go up 2, right 1, up 2, and right 1. And I'm going to go backwards just to get a few extra points. So down 2 and left 1, down 2, left 1. For this line, since I have a greater than or equal to sign, I'm going to connect the dots with a straight, solid line. So now I'm going to do the shading. I can use my 0 and 0 point since it does not lie on my line. So my x is going to be 0 and my y is going to be 0. So when I plug in, I'm going to have 0 is greater than or equal to 2 times 0 plus 6. Well, 2 times 0 is 0, so that will cancel out. And I have 0 is greater than or equal to 6. Now I need to determine if this is a true or false statement. Since the inequality is eating the 0, it means that 0 is bigger than 6. We know this to be a false statement, so I'm going to shade above my line. Now I can graph my second equation. So my slope in this equation is m equals negative 3 over 4. I moved the negative sign up with a 3. That way I know to go down when I perform my slope. My y-intercept is negative 5. So to start, I'm going to graph my y-intercept at negative 5 on the y-axis. And then I can do my slope. So down 3 into the right 4. Like last time, I'm going to go in reverse so I can get a few more points. So I'm going to go up 3 into the left 4. Now these two lines do not have to intersect at a perfect point. You can see here that they definitely are not going to. It's the shading that we are most worried about. So with this line, I need to have a dashed line since it's less than or equal to. 0 and 0 will work again for my shading. So when I plug in, I'm going to have 0 is less than negative 3 over 4 times 0, subtract 5. Negative 3 over 4 times 0 will cancel out, and I'll be left with 0 to be less than negative 5. This time our inequality is eating the negative 5, so it's saying that negative 5 is bigger than 0. We know this to be false as well, so I'm going to shade below my line. Now when we do our shading, I know it becomes a challenge when we have more than one line on a graph, but you want to shade and pretend that you only have that one line. So everything below that line, even when you overlap, gets shaded in. Now that we have our shading done, we can see where the two colors overlap, and that is our solution area for our entire system.